Good morning, dear students. Our next session, that is regarding the partial ionic character of the covalent bond. Okay. So normally, for example, for a covalent bonded compound, that is, for example, hydrogen molecule, that is H single bond H, then chlorine molecule Cl single bond Cl. These molecules, they are having pure covalent bonds, isn't it? They are having pure covalent bonds. That means the electrons are shared equally between these two atoms, isn't it? That is, there is no difference in the electronegativities. Okay. No electronegativity differences are there between the two atoms. That means two similar atoms are joined together with the help of a covalent bond. So no electronegativity differences are there, and also the sharing of the electrons, the sharing of electrons, it is done mutually, and the sharing of electrons, it will be the same for both the atoms, equally shared by the two atoms, isn't it? And also we can say that the molecule, it is symmetrical, isn't it? If we are cutting this molecule at this point, what happens? The two electrons are equally shared between the two atoms, isn't it? So they have got a pure covalent bond, and also the molecule is symmetrical. And also the electron charge cloud will be shared equally, or it will be distributed equally between the two atoms. Okay, but see, in the case of a carbon hydrogen bond, see, the one of the element, the bond is the covalent bond, it is formed between two different atoms, isn't it? One is carbon and the other is hydrogen atom. So here there will be a slight electronegativity difference between the two atoms, isn't it? Carbon will be somewhat more electronegative, isn't it? So slight electronegativity difference will be there between the two atoms. And as a result, what happens is that there will be a already there is a covalent bond. A slight electronegativity difference will be there, and as a result of this electronegativity difference, what happens is that the shared electron, it will be shifted preferentially towards the more electronegative atom. Okay, so in this carbon hydrogen, or another example, OH, oxygen, one of the atom is oxygen and the other is hydrogen. That means two dissimilar atoms are there. So in the case of such type of bonds, what happens? The electron distribution, the bonding electrons are not shared equally between the two atoms. So what happens is that the electron pair, the bonding electron pair, it will be shifted more towards the more electronegative atom. Okay, there will not be a pure ionic bond. Only the bonding electron will be slightly shifted towards the more electronegative atom. So as a result of that, a partial ionic character will be developed, isn't it? So ionic character means the electron will be completely transferred, but here the electron is not completely transferred. Only a slight charge separation will be there, or the bonding electrons will be shared unequally between the two atoms. So the electron shift will be towards the more electronegative atom. So that particular atom will be getting a slight negative charge, and the other atom will be getting a slight positive charge. So this slight negative and slight positive charges are denoted by delta. Okay, so this is the case of the partial ionic character of a covalent bond for dissimilar atoms. There the electronegativity difference occurs in the case of dissimilar atoms, and as a result this partial ionic character develops. So such type of bonds, we can call it as a polar bond, isn't it? That means a polarity, slight polarity is developed between the two atoms. Okay, so the bonds are polar here in this type of molecules. Bonds are polar. And also see here this partial ionic character. So here we can say that in the case of OH bond as well as in the case of CH bond, we can say that these are all polar covalent bonds. That is, the bond is formed, there is a pure covalent bond, but what happens is as a result of the slight electronegativity difference between the two atoms, what happens? The shared electron pair will be shifted somewhat towards the more electronegative atom, and as a result a partial ionic character develops, and as a result we can say that this bond, it is a polar covalent bond. And also this partial ionic character of the covalent bond, it depends upon two factors. The first one, that is the electronegativity difference. I am writing it as En. Sorry, electronegativity difference. The first one, it is due to the electronegativity difference and partial ionic character. Partial ionic character. Electronegativity difference and the partial ionic character. See here, if two similar atoms are there, for example AA, that means there will be no difference in the electronegativity. Both the atoms are similar, so they have got the same electronegativities, and as a result, the bond formed as a result of these two atoms having same electronegativities, we can call it as a non-polar covalent bond, isn't it? Here no electronegativity difference are there, two similar atoms are there, so the bond formed will be a non-polar covalent bond. But see, in the case and in the second example, that is AB, two dissimilar atoms are joined together, and if this B, it is slightly electronegative than A, then what happens, this electron pair will be shifting more towards B, so B will be having a delta negative charge, slight negative charge, and A will be having a slight positive charge. Okay, so as a result, what happens, there is an electronegativity difference here in this case, and as a result, the bond formed will be a polar covalent bond. Polar covalent bond, and also the bonding electron, it is shifted towards the more electronegative atom. Then again, see here, as the electronegativity difference increases, what happens, the polarity of the covalent bond also increases. Okay, so as the electronegativity difference is increased, what happens, the polarity of the covalent bond will also increases. Okay, that means the intensity of the charges will increase. If the intensity of the charges increases, means the polarity of the bond also increases. So greater the polarity, what happens to the ionic character? Ionic character will also be increased. Okay, so that is the point to be noted here. The greater the electronegativity difference between the two atoms, the polarity increases. As polarity increases, the ionic character also increases. So next is a relation connecting this ionic character, relation connecting ionic character and electronegativity. Ionic character and electronegativity. So this equation, it was derived by Pauling, and hence the equation, it is called as Pauling's equation. Sometimes you have studied in your first sem, isn't it? So the relation between ionic character and electronegativity devised by Pauling. And also here, see the equation, it is like this: the amount of ionic character, it will be equal to 1 minus e raised to minus 1 by 4 into chi a minus chi b the whole square. Okay, the amount of ionic character is equal to 1 minus e raised to minus 1 by 4 into chi a minus chi b the whole square. So, and also it is represented simply by using this equation, that is 1 minus e raised to minus 1 by 4 into chi a minus chi b the whole square. What is chi a and chi b? Chi a and chi b are the electronegativities of the atoms A and B. Okay, chi a and chi b are the electronegativities of the two atoms A and B. So chi a minus chi b gives the electronegativity difference. See, it is an exponential value, isn't it? See, this difference, it will be an exponential value. So in a table, we can write this electronegativity difference briefly. So this is chi a minus chi b, the first row, and the second row, it is percentage of ionic character. Okay, percentage of ionic character. So if the chi a minus chi b difference, or the electronegativity difference, if it is 1, then the bond, or that particular bond, will be having 20% ionic character. Okay, if the electronegativity difference, if it is 1.5, then the bond will be 40% ionic. If the electronegativity difference is 2, the bond will be 60% ionic, and if it is 2.5, the bond will be 80% ionic. Okay, so this is a brief method by using this equation. Okay, 1 minus e raised to minus 1 by 4 into chi a minus chi b the whole square. So for any atoms, if you are knowing the electronegativity difference between the two atoms, we can roughly say that the percentage ionic character of that particular molecule, it will be molecule or bond, it will be 60%. Okay, so this is how we have to calculate the amount of ionic character. Then the second one, see here, the first factor favoring this partial ionic character, that is the electronegativity difference and the partial ionic character. So the second one, that is the dipole moment and the partial ionic character. Okay, second one, that is the dipole moment. This is very important, partial ionic character of covalent bond. Dipole moment and partial ionic character. Dipole moment and partial ionic character. See here, the dipole moment, normally what do you mean by dipole moment? It is the product dipole moment denoted by the letter mu, isn't it? Dipole moment mu, that is equal to product of the charges at one pole and the distances between the two poles. Okay, dipole moment, it is the product of the charges at one pole and the distance between the two poles, that is mu is equal to q into distance. That gives the dipole moment. Okay, see for a molecule having dipole moment, what happens is that the relation connecting dipole moment and the partial ionic character is that with the greater dipole moment, what happens, the charge separation will be greater, isn't it? So if dipole moment is larger, what happens? The percentage ionic character will also increase. The percentage ionic character will also be greater. Okay, so for larger dipole moment values, the percentage ionic character will also be greater. That means, see, larger dipole moment means the charge separation. So these are the two point charges separated by a distance, two opposite charges separated by a distance d, and if the charges are greater, what happens? If the charges are greater, what happens? The dipole moment will be increased, and if the dipole moment is increased, the ionic character will also increase. Okay, then there is another relation for calculating the percentage ionic character. Another relation for calculating the percentage ionic character, and the relation, it will be like this. The formula is like this. The percentage ionic character, it will be equal to the actual dipole moment divided by the dipole moment of a pure ionic bond. Actual dipole moment divided by the dipole moment of a pure ionic bond into 100. Okay, so this relation gives the percentage ionic character. This is another relation connecting dipole moment and percentage ionic character. In the previous portion, we have seen the relation connecting percentage ionic character and the electronegativity difference. Here it is the relation between dipole moment and percentage ionic character. So this will be equal to actual dipole moment divided by dipole moment of the pure ionic bond into 100. Okay. So some values are given in your textbook also, and one of the example I will be illustrating here. See, for example, HF molecule, the dipole moment of the observed dipole moment of HF molecule observed dipole moment of HF molecule, it is 1.98 debye units. The unit for dipole moment is debye, isn't it? So the observed dipole moment for HF is 1.98. And also the actual dipole moment, or the dipole moment observed from the structure of HF molecule, that will be equal to 4.44 debye units. Okay, so the observed dipole moment, it is 1.98, and the actual dipole moment, that is for the ionic species, it will be equal to 4.4 debye units. Therefore, we can calculate the percentage ionic character of this HF bond. Percentage ionic character of HF bond, it will be equal to, what is the formula? Actual dipole moment divided by dipole moment of the pure ionic bond. So here the actual dipole moment or the observed dipole moment, it is equal to 1.98 divided by the dipole moment of the pure ionic bond, that will be equal to This is not the actual, this is the dipole moment of pure ionic bond. Okay, dipole moment of the pure ionic bond. So 1.98 divided by 4.4 into 100, and the value it will be equal to 45% ionic. That means it has got almost 50% ionic character as well as 50% covalent character. So HF bond will be almost a bond having both ionic character as well as the covalent character. See, 45% ionic character means 55% it will be having covalent character, isn't it? So for HF bond, it will be having 45% ionic and 55% covalent character. So this is how you have to calculate the dipole moment. Okay. So then the next one, that is the dipole moment and geometry of molecule. It is very, very important. See, these portions are very, very important in this chapter. You should not omit any of the portions. Okay. It will be the questions will be asked from anywhere of this part. Okay. So dipole moment, it is also a very important topic. Then the next one, that is the dipole moment and geometry. Dipole moment and geometry of molecules. See here, dipole moment. See, for a molecule, if the dipole moment of a particular bond, if it is say for example for OH, means it is a that particular bond has got a ionic character, isn't it? And also this particular bond has got dipole moment also. So if a bond is having dipole moment, then what about the case of the molecule? The molecule will also be having dipole moment. Okay. If the bond is having dipole moment, then the molecule will also be having a dipole moment. So if a diatomic molecule is polar, means a polar diatomic molecule means the bond will also be polar, isn't it? For example, we have seen HF molecule. See, HF molecule, the bond is polar, then the molecule will also be having polar nature. Okay, so if the bond is polar, then the atoms will also become polar. Okay, then and also again this dipole moment, it will be depending on the polarity of the bonds, or we can say that dipole moment of a molecule, it will be depending on the dipole moment of the bonds. If the bonds are having dipole moment, then the molecule will also be having dipole moment. Then the second point is that the spatial arrangement of the bonds, this dipole moment will depends upon the spatial arrangement of the bonds. Okay, or spatial arrangement means the geometry of the molecule, isn't it? So dipole moment depends on both these two factors. That is, it depends on the dipole moment of the bonds as well as the spatial arrangement of the bonds or the geometry of that particular molecule. Okay, so we can say that this dipole moment will helps to predict the geometry of the molecule. Okay, dipole moment helps to predict the geometry of the molecule. So this is very, very important. Dipole moment helps to predict the geometry of the molecule as well. Okay, so we can go through some of the examples for the dipole moment and the geometry of the molecule. Say for example, carbon dioxide, CO2 molecule. Okay, CO2, the structure, it will be like this: C double bond O, C double bond O. See, what about the CO bond? There is an electronegativity difference between carbon as well as oxygen atom, isn't it? See, an electronegativity difference is there. See, according to our previous portions, if there is an electronegativity difference between the atoms, the bond will be polar. Okay, so here the bond is polar and hence the bond is ionic. But see, what happens is that, see here, the molecule has a geometry, linear geometry, isn't it? Linear geometry. And for the CO bond, the electronegativity difference or the dipole moment, it will be equal to 2.3 dB units. Okay, that means the bond is ionic, or it will be having dipole moment, or it will be having polarity. So as per our theory, we can say that it should be this carbon dioxide molecule, it has got two CO bonds, isn't it? One CO bond and the second CO bond. So it will be having definitely it should be having some polarity or ionic nature. But actually, see the structure, it will be like this. It has got a linear geometry, and as a result, the polarity or the dipole moment of one CO bond, it will be exactly cancelled by the dipole moment of the second CO bond. Okay, that means the dipole moment of the CO bonds gets cancelled each other, since the geometry of that particular molecule, it is a linear geometry. So we can say that this CO2 molecule, even though the CO bonds are polar, CO2 molecule as such, we can say that it is a non-polar covalent molecule. Okay, CO2 molecule, it is a non-polar covalent molecule, and also for CO2